And so welcome everybody to the start of Big Data today. I'm gonna share my screen here. And today, this week, we're gonna be starting, I've got a new week 5 folder for us to be going over this week. And the basic idea of this week is we're gonna be talking more about designing the database and why you might choose your tables to be arranged in a certain way and have the columns that they do. And so the past 2 weeks, we've been talking more about SQL that is both general purpose SQL for any database system. And we've also been focusing more on the just correctness aspect of SQL, making it do the correct thing. And at this point, we're going to be starting our transition both into really Postgres specific stuff, Postgres specific details, and into the how to make it fast or how to make it efficient for whatever measure of efficient. And in particular, the efficiency that we'll be talking about this week is our disk usage, like how many bytes on the hard drive is our database taking up, and what are the things that we can do to make that more efficient. Let's see, two quick announcements. The first one is that we're currently about 1 week ahead of schedule, which is good. So the due date for my wife's pregnancy is next week. So probably here pretty soon, the baby will come and we'll take a short break from Big Data. But we're doing good time-wise. Because of being ahead of schedule, we've been going super fast through all of the material, kind of been sprinting through it so far. And we've also, I know it's been a sort of weird semester with the starting online, going in person. And so I have just a quick survey here that takes you if you were to click this link, it takes you to the issue that explains it. Here's the link to the actual Google form. And it's just some short questions here that I would appreciate if you fill out and give me some feedback on how the course is going for everybody. Any questions? Well, let's see. So also at this point, the first Pagilla homework sort of nominally due last night. But again, if you collaborate with other people, then you have until tomorrow to complete it. And so typically for all of these assignments, I'll be grading them on after the Tuesday deadline, after the collaboration deadline. And so next Wednesday, we'll have a chance to go over how everybody did. But there's a lot of submissions so far for that first assignment. Any questions about anything administrative-wise for the course? Sam?
2 questions. Just confirming the take-home quiz is due Wednesday, correct?
Oh, yes, great. Thank you for reminding me. So last week, we're not, so normally we would be having sort of quizzes throughout this SQL time period, but I've decided since we're going at the accelerated pace and for various other reasons not to have the quizzes actually be like quizzes in class, and you have the take-home assignments that you complete. And Wednesday, so next class session is when that take-home exercise is due. And again, you're welcome to use whatever resources you want, collaborate with other people, use computers, anything else. Let's see, questions just about the take-home assignment at this point? Axel.
Do we hand it in a physical copy?
And yeah, so please write the answers physically on the paper and then bring it with you on Wednesday and turn it in.
Okay. If we collaborate, do we get an extension on that as well?
No extension on that one. Yeah, that one's just due on Wednesday. Any other questions about the take-home assignments? Great. Sam?
Yeah, other question was on the Pagilla homeworks. I know homework number 2 was posted on week 4, but homework number 1 was the one due this week, correct?
Correct, yeah. So the homework 1 is the one that's the deadline is yesterday. The Padilla Homework 2, we've covered all the material for that at this point. Here in a minute, we're going to start class by doing just another one of the review problems. We're working through one of those problems related to the unnest function. But that homework assignment, the Padilla Homework 2 assignment, is due this coming Sunday. And I realize that's all a little bit confusing because of the way the lectures are a little bit compressed. So yeah, good question to clarify that. Any other questions about anything administrative or content? Any questions at all at this point?
So what's the class structure going to be like when your baby does come?
So yeah, when the baby comes, which I don't know the exact day, only the baby knows, we'll have some period of time off, depending on exactly when it happens. It could be up to 2 weeks of classes off, and you'll be able to work on assignments and things like that. And then we'll pick up at some point, like back to normal class in person and all of that. So it'll just be like a pause in the class. Okay, great questions. So again, before we get into like the new material starting today, I wanted to do just review this unnest function. It's one of the sort of both cooler functions and a little bit weirder functions of SQL. And last time we talked about just sort of the unnest function, sort of like in theory, but we didn't actually see how it applies to the Padilla Homework 2 assignments. So that's what we'll do today. So in the SQL folder, number 8 and above, use the unnest function. And so let's go ahead and open up that one. And the idea here is we want to select the title of all G-rated movies that have the trailer special feature. And actually, I also want to, we want to have both our windows open. I mistyped that. So move that to our Padilla Homework 2 folder as well, make it a little bit bigger, format it nicer, and reset it. And then up top, Control R, then pSQL to enter into pSQL like this. And so we need to, so the G-rated movies that have the trailer special feature. We do \D, film is our table that has all the films. And there was this special features column. The special features column is an array of text. We know it's an array because it has these 2 square brackets right here. And then text is basically just strings. And so real quick, I'm going to do a select star, not select star, select special features from film just to get a sense of what kind of things might be inside of here. And we saw last time about the syntax of arrays. There's multiple different kinds of syntax that will appear at different points. But these curly braces are one of those syntaxes. And inside of the curly braces, it's the double quotes that indicate the content of the entry of the array. So this array right here has 2 entries. It has deleted scenes and behind the scenes. This one here only has 1 entry. This one only has 1 entry as well. Some of these actually, so we didn't see this last time, I don't think. Some of these have no quotation marks around them. If it's only a single word inside of here, it doesn't need quotation marks at all. So lots of weird things, lots of weird things. And then the unnest function. Well, let's see, maybe first before the unnest function, if we do title, comma, special features, we'll have these 2 columns. Here's the title of the film on the left. Here's the special features array on the right. And recall that the unnest function, what it does is it takes each of these array entries and puts it on its own row. So here we have Academy Dinosaur as 1 row with these 2 special features combined in the same row. But then when we do unnest of special features like this, then we have Academy Dinosaur, 2 separate rows with each of the entries of the array like this. Whenever you have a function call inside of Postgres, it's going to name the column by default, just the name of the function. That's not a super nice name, so let's name that as special feature. I like to make the result of the unnest being singular and the column names that are arrays being plural. So that just gives me a hint that if something's plural, then it's got multiple things inside of it. But I've made it singular at this point because it now only has one special feature per entry. And it's asking that we find the title of all the movies that have the trailer special feature. So let's queue up here. And so we'll add where special feature equals trailers like that. And so we ran into this problem last time too, that when we do this unnest function like this, we can't actually refer to the result of this unnest call inside of the where clause. Instead, I have to use the subquery. Pretty much anytime you have an unnest call, you'll have to use a subquery. And so my query is starting to get a little bit big up here, up top now. So I'm going to enter vim \e. Again, \e takes whatever your previous query was that you were running and puts it inside of vim so that we can edit in a little bit nicer environment. And we'll do a select star from this big thing over here. Anytime we have a sub query inside of the from clause, we have to name it. So I'll name it T. And then we do where special features equals trailers like this. In general, I said that select star is a sort of bad practice. In this case, though, because I know like exactly what the titles are right here, it's fine to use select star. I only avoid select star when the thing inside of the from clause is actually like the name of a table where maybe I don't know what those columns are actually going to be. But here, since the columns are listed right here, select star is fine, and it makes it just a little bit nicer to work with. So escape :WQ, save and quit that, run it, and now we have all of these titles and special features right here. I'm going to at this point look down back at our problem down here, and it says we need to so we have the title of all of the G-rated movies that have the trailer special feature. So the only thing that's not here at this point is that sort of filtering these for all the G-rated movies, that this is all of the movies total. And we'll have to filter this so that it's only the G-rated movies somehow. And we'll do that next. But before doing that, any questions just on this unnest, what we've done so far for that? Okay. Then what we need to do, so I'm going to take another look at the Padilla homework. I want to take a look at the schema down here. And so we have the film, and let's see. Okay, so we have rating down here is actually an entry in the film. I don't even have to do any joining to get the rating. So \E, back up here, let's change this to title and rating, like that. And now we have our ratings here. So I just now need to add a second where clause on the rating, where rating equals G, \E, where special features equals trailers, and rating equals G, like that. Escape :WQ, save and quit that. And now we have the all the ratings are Gs, all the special features are trailers, and we have the titles over here. In the actual results, let's take a look at what we're expecting to get. So I'll go results, and then this was problem number 8. So 08.out. Oops, no. And again, results is the actual output that you got, and we haven't run our check answer script yet, so that's why this file is empty. And so I was meaning to go to the expected, what are we supposed to get? And here we can see that there's only the title column here, no rating and special features columns. And so in order to fix this, Q \E, I need to, instead of selecting star, instead of selecting all of these columns, now I have to go in and actually specify a column title like this. And it's also any of these problems, you'll want to have it ordered so that it's deterministic results. And let's see, wants the results ordered alphabetically. So let's add order by title right here. Save that. And now these, I believe, will be a fully correct answer. Any questions about that problem or my thought process in going through and solving a problem like that?
So I was getting different number counts for some of the problems on the homework, last homework. And even though I was and I'd get different number counts based on where I started. In sort of the, let's say if I had to connect like 5 different tables together, if I started from one end and connected them forward, I'd get a different number than if I started from the other end and connected them that way. If that makes any sense. How that would be the case.
Let's see. Yeah. So the question is more general than just this problem, but if we have a bunch of tables that we're joining together, and so if we go back over to here, so say we're joining like category up to inventory, following this path right here. If you go category, film, and inventory, or versus inventory, then film, category, and category. And well, you get different results depending on which order you do it in. If you're using an inner join for all of those joins, it shouldn't matter like which direction you go. But if you're using a left join or any of the outer joins, then the directionality will matter. And the left join from category up to inventory would be the same as like right joining from inventory up to category. Are you saying that you were getting with inner joins different results, or was it with the outer joins?
Like a couple of like dollars differences in my results, and it was when you were calculating some of the things stuff. But one of them was, but it was just all to see that like I didn't know that like that would be different. Wait, when you do a regular just right join, is that left join by default?
If you say join by itself, that defaults to an inner join.
Okay, then yeah.
Yeah, so it is possible to take like different routes through these mappings that have different semantic meanings, and depending on like the route you take, you'll get different results. When we're talking sort of through this week's lectures about why you would design, like why do they have these separated out into different tables, then we'll be talking a little bit more about the semantics of all of this, and then that might make it clear why certain paths are the right path to do. Dustin?
Where you were just doing, can you do that without I was wondering if you didn't do a subquery, if you just selected some features and the rest of those, it would work.
So the question is, here I'm doing a subquery, and is that subquery actually needed? And the answer is, I believe so. I'm sure there's ways to write this without using a subquery, but because I'm using this unnest function right here, and because my where clause is specifically wanting to refer to the result of this unnest function, that's the key like indicator that it should be in a subquery. Pretty much any time you're using the unnest function, you'll want to also be using a subquery.
Is it possible for a where clause to check if a value's in an array without like unnesting it? So, for example, like checking if trailers is in the special features array.
Yeah. So the question is it possible to not use this unnest clause and just check to see whether trailers is contained in special features? The answer is yes. I think in last week's notes, there's a link to the Postgres documentation for the array type, and it has a whole bunch of built-in operators. Off the top of my head, I don't know how to do it though, because it turns out to be array indexing for text types is an O of N operation, and unnest is going to be a constant time operation. So vast majority of times, unnest is the thing that you want to do. The other sort of operators are there so that people who are not like in this SQL mindset of making subqueries and filtering like this can use the more like imperative approach that you might be more familiar with in like Python or other programming languages. And we will actually be using those a little bit later, but in-nest is sort of the go-to thing. And so, yeah, so in particular for all of these problems, 8 and on, you'll want to use unnest in a subquery. And they're all related to this special features column. Great questions. Any other questions about the Pagilla homework number 2? Okay. As you're working on it throughout the week, if you do have any other questions, feel free to come by office hours, ask me after class, ask me during class, or post things to GitHub. In general, you shouldn't be like shy about posting things to GitHub. It's totally okay to post like a fully correct answer and just ask a question like, this is correct, I have no idea why it's correct though. Or yeah, you should never feel shy about like posting too much on GitHub. It's always okay to post things on GitHub. Okay, so today, again, talking about designing the database layout, both the semantics of it and the like actual nitty-gritty under the hood. And so our goals this week, the main goal is to measure the disk space usage of a database. And there's 2 reasons why the disk usage might be more than you might expect. One is that there's just a certain amount of overhead that is unavoidable. It's a little bit bigger. Overhead that's unavoidable. And there's 2 different types of overhead, row overhead and page overhead that we'll talk about. Today in class, we'll start with this row overhead. And then also, you might just be storing more data than you need to be doing, storing things redundantly. And then, not today, but probably Wednesday, we'll talk about these other miscellaneous design decisions that you can make in a database. And this will be going over that semantics question of like, why are those tables, why are those the right tables for the Pagilla database? So specifically for the midterm, like what to keep in mind while we're going over the lecture today, you are responsible for being able to calculate the number of bytes used by a row of data. And there was a handout today. If you didn't get it, it's in the back, and it corresponds to this tuple size notes.sql file. This is one that you could enter it into Postgres and run it, but we're not going to do that in class today, so don't feel a need to like try to download this and get it into the right folder or something. We're just going to be like working through these by hand of calculating exactly, okay, we have a table, has some structure, how many bytes does that particular row take up? And this will be important. Well, so I guess the most proximal reason, again, why it's important is your midterm will have problems that look just like this that you'll have to complete. But more like actual real world, we'll see that the overhead can potentially be very large, like up to a factor of 10. And so if you have 1 gigabyte, that explodes to 10 gigabytes of actual on-disk usage. And so you want to avoid those situations, and we'll learn how to avoid those situations. But another problem with that overhead, besides just disk usage, because disks are cheap, it's just less than $100 for 10 terabytes of disk these days. So even if you explode things by a factor of 10, that's not too big of a deal. But if you have 10 times more disk usage, then things are going to be 10 times slower as well. So by reducing the amount of bytes used, we'll be making things faster as well. These are the 2 references that if you want to, maybe something in lecture didn't fully click, you'll want to reference these. And I'll also say that all of the problems that you'll be doing on the upcoming homework assignments and like midterm problems that are related to this section here, these links actually contain SQL queries that you can just type in and it will tell you the solution. So you'll type in that this is what my table looks like, this is what my insert looks like, and it will tell you how many bytes it takes up. So you can, I'm not going to show you those commands, but you can look them up there if you want. A little bit of maybe just real quick background. So Postgres, mentioned this a while back, but it's a little bit famous for having a lot of overhead compared to other databases. And that overhead is related to like the correctness emphasis of Postgres. Other databases may be emphasizing fastness or less disk usage, but Postgres emphasizing correctness. And then each one of these rows, and sometimes in the notes, and sometimes on the links, and sometimes in my voice, I will say rows, sometimes I will say tuple. Row and tuple are interchangeable, they mean the same thing. So each tuple is divided into 3 sections, a header section, a data section, and a padding section. In the header section, there's always going to be a 23-byte struct called heap tuple header data. And if you click this link, it takes you to an actual description of what all of these bytes are doing. We'll talk about a lot of these bytes when we talk about something called transactions in Postgres. But at this point, the important thing is just that there's a 23-byte overhead that every row is going to have. After the 23-byte overhead, there is an optional thing called a null bitmap that may or may not exist. The null bitmap is only present if the tuple contains at least 1 null value. And then the bitmap uses 1 bit per column, where the column is either nullable or not nullable. This is a little bit confusing right here, because if we look at this example table right here, we would say these two columns right here are nullable because they can contain null values. This null keyword right here is optional. It means the exact same thing as leaving it out. So both A and B can contain a null value. C cannot contain a null value. But the C column still is counted in this null bitmap. The reason that's important is because the total number of bits is the total number of columns. And after we go over 8 columns, something moderately bad is going to happen. We'll have the bad thing that's going to happen is that the header must be padded to be a multiple of 8 bytes. And so if we have 9 columns, then we'll have 9 bits that we need. 9 bits is we'll need 2 bytes for that. And so we have 23 bytes plus 2 bytes is 25 bytes. Rounding that up to the next multiple of 8 is 32. So for any table with less than or equal to 8 columns, you'll have maximum 24 bytes overhead, because the null bitmap is only 1 byte. But for any table with more than 8 columns, so 8 to 264 columns, you'll have a 32-byte overhead, because the null bitmap is greater than 1 byte. This is, there's going to be a lot of maybe sort of just dry background information of going through all of this, and then we'll hit the problems once we've talked about all these details, and that will hopefully make things a little bit more concrete. But any questions about this header section of the heap tuple header data or the optional null bitmap? Okay, again, the main takeaway is these 2 points right here. You're going to have either 24 or 32 bytes in the header in the vast majority of cases. The data section is sort of the most important one. So every one of your columns that has a non-null value will require a number of bytes depending on the column type. There's a lot of column types in Postgres. We'll see how to list them all here in a second, but here's some of the common ones. So there's various different integer sizes that you can use depending on how many bytes of data that you need, floating point bytes, and then text is variable so that you can store arbitrary length text. One of the nice things about Postgres compared to other database systems is that there's no limit on the size of text that you're inserting into the database, and you don't have to, and there's no overhead about like storing extra large text. If you're using MySQL or Oracle or any of these other databases, you have to somehow structure your table in advance so that it's going to contain enough space for different sizes of text, and you're going to pay a pretty steep penalty for that. But you won't have to do that in Postgres. We'll talk about exactly how these variable types are handled later, but the most important thing is that just these small basic types are going to have some fixed amount of size like this. Whenever you have a null value, that's going to consume 0 bytes of disk space. So if we have a big int that's null, something like, so an integer that's null, if this integer is present, it consumes 4 bytes of disk space. If it is not present, it consumes 0 bytes of disk space. I think most students tend to find like everything that we've talked about so far roughly, I know it might be like just a lot of gibberish at this point, but like once you work some problems, that makes sense and is pretty easy to get a handle of. But this alignment issue is often a tricky thing, especially for the people coming from the like the data science track instead of the computer science track. And the reason for that is that the hardware courses in the computer science track probably have covered this before. But due to various weird hardware implementation details, every different type has an alignment that it has to like sit in the in memory. And usually this is let's see, I'm gonna switch over here, open up Vim, and do an example of what this alignment is going to look like. It's bigger and just one Vim window. So if we have a 64-bit machine, so the Lambda server, basically all computers made this these days are 64-bit machines. So that means 64 bits, 8 bytes, and all data somehow has to sit in a memory address that is aligned to 8 bytes, or the memory address of data must, whatever the memory address of data is, if you mod it with 8, must be equal to 0. And so for the big integer type, big integer, it has, its size is 8 bytes. And so this is never going to be a problem. If we have, say, like 10 big integers next to each other, 10 big ints, then they're always going to be aligned one after the other. Their position in memory is always going to be mod 8 equals 0 because they're 8 bytes in total. But if you have something like a small int followed by a big int, the small int is 2 bytes. The big int is 8 bytes. And so in order for, if the small int is at memory position, say 16, the small int is at memory position 16, then the end of the small int is memory position 18. And so we can't just put the big int right next to the small int because 18 is not divisible by 8. And so we'll have to add padding, add 6 bytes of padding so that the next memory position is 24. 24 is divisible by 8, and so the big int could be placed at memory position 24. Normally, yeah, I would draw a little picture of this, but since we don't have a camera on the whiteboard, I don't want to do that because it won't appear in the Zoom. But anytime you have a type that is smaller than what its alignment is, then you'll have to add padding so that the next type can be aligned at the right position. We'll see more examples of this that will hopefully make that clearer if that's not fully making sense at this point. To find information about a type, so the type name, the alignment, and its size, this is the particular query that you'll want to run. This PG type table is built into Postgres, and so you can run this on any database. So I'll just come over here. Here we go. Open up pSQL, paste that command, hit enter. And you can see there's a lot of different types that are listed here. Press Shift G, take me to the bottom. 667 different types built into Postgres. The type name is the thing that you would be putting. So type name is the thing that goes like right here after the name of the actual column. Type align has different characters that correspond to a number of bytes that the alignment must satisfy. So down here under the documentation, so this is the query that we just typed into Postgres. Under the documentation for the PG type table, it's this link right here. I have it open up here. There is this type align care column. So type align is the second column in the output of this query right here, type align. And the type align can have these values right here, C, S, I, or D. These are the required alignments of the particular type. And C means that the type can sit anywhere in memory. S means that the type must be in a memory position where %2 equals 0, I %4 equals 0, D %8 equals 0. So armed with this, I'm going to quit out of this, FG back into here. For the small int, the type align, I think there's no E right there. Type align equals S for short is 2 bytes. S equals 2 bytes. And so that means that every memory position must sit at something mod 2. And so if we have, we're at our small int at memory position, small int at memory position 24, then it goes from 24 up to 25. So it takes 2 bytes, has an alignment of 2 bytes. And so we can put another small int at position 26 because 26 %2 is equal to 0. And the type align of small int is 2 bytes. If we were to put an integer after small int, integer has a type align of I, which is 4 bytes. Integer type align equals I is 4 bytes. So if we have, again, the small int at memory position 24 to 25, the next position that we could put an integer at would be 28, because 28 mod 4 equals 0. We couldn't put an integer at 26 because 26 mod 4 is not equal to 0. And so if we ever have a small int followed by an integer, we must add padding bytes to make the next position be 28. Again, if this is all seeming like a lot of random numbers, once we've seen all the stuff that we need to see, we'll turn to the problems, and that will hopefully start making things more clear. Dustin?
So how does it do this when you insert padding, right? Or you include padding? So like, if that makes sense. So like when you had like 6 bytes adding to the next 24, like how does the computer know that you had 1 2 byte value, right? It's a small byte.
Let's see, why don't we switch over? So the question is basically, how does the computer know that it needs to do this? Let's switch over. We've seen enough now to cover the first 2 problems in the handout over here. So we're gonna talk about these first few problems, and I think that will start making things a little bit more concrete. So here in this first problem, we have, I'm going to copy and paste that here. So the header always 23 bytes for the that heap tuple struct. And then in this case, the bitmap is going to be 0. No null bitmap, because there's no null values. This 23 bytes, the size of the header must always be a multiple of 8, so we have to pad it, adding an extra byte. So the final size will be 24 bytes. Again, 24 is going to be the most common value for your header. The data here has 1 integer. The integer takes 4 bytes. So it'll be 4 bytes just for this 1 column. Because there's only 1 column, we don't have to worry about the padding part of the column with another column happening after it. But this last padding field right here, the entire size of a tuple must be a multiple of 8. And so if we added 24 plus 4, that's equal to 28. In order to make this a multiple of 8, we need to add 4 bytes of padding. So we get 32 bytes total. So 4 bytes for the integer. The data section is only 4 bytes. And then this padding is so that the entire row gets up to a multiple of 8, adding 4 to our, so 24 for our header, 4 for our data, plus 4 for the padding is 32 total. Yes?
Does it matter what order the columns come in? So if we have like small and small, does it know?
Question is, does it matter the order of the columns? And the answer is yes. We'll get to that in the next examples. So at this point, there is no way of ordering the columns because there's only 1 column, and so ordering doesn't matter. Yes?
Is the size of the header the same for each row across the table?
Yes, the question is the size of the header for each row across the table? And the answer is yes. There's an additional header for the table itself, which we'll talk about later. But this header is for every individual row that gets inserted. It has this 23 byte struct header. It's possible, and at the very end, we have an example where some rows will contain the null bitmap and some rows will not contain the null bitmap. And so the size of the actual header itself will be different depending on the row, but they will all have some header, and it will all be at least this 23 byte size. So next example, inserting a null. Now we have the 23 byte struct. We have a 1 byte null bitmap. Up here, no null bitmap because no null values. Here, yes, null bitmap because we do have a null value. And 23 plus 1 equals 24 happens to be the same size as this one up here. So if you have less than or equal to 8 columns, your header is always going to be 24 bytes, whether you have null values or not. The data in this case has nothing. Null values take up no data, no space. And so this is 0 bytes. The padding, if we add 24 plus 0, that's still equal to 24. 24% 8 is still 0, so no padding. And so the total is 24 bytes. So these two examples right here only have one column, and so there's no nothing tricky about the padding going on here or the alignment going on here. The next example, though, has 2 columns or 3 columns, and so we'll see the issue of alignment come up. And again, that's probably the more tricky part. But any questions about any of these things before we get into the second example that has the alignment, Joey?
On the first example, could you go over why it ends up being 24 as the final bytes, given that there are no bitmap?
The header always must be a multiple of 8.
Okay.
And so because it must be a multiple of 8, we just have an empty byte even without the null bitmap. Yeah.
I'm not sure if this makes sense, but are we saying that like each row has a header?
Exactly. Every row has a header. Every row has all 3 of these components: the header, the data, and the padding.
Is that a padding as well in the third example where we have a 33 byte struct and it's the additional 1 byte considered as a padding or sorry, the example of the first one.
So yeah, no null bitmap. I'll type it out. So 23 byte struct, no null bitmap because there's no null values. So we pad the 23 bytes to 24 bytes because it just must be a multiple of 8.
That doesn't concern with the padding below, right?
And that's different than this padding section here. Yeah. The word padding is going to come up multiple times, many different places. It's just any time that you're adding bytes to something that don't really have any particular meaning, they just have to be there. We'll call that padding. Any other questions about this example 1 table?
So why is there 23 bytes? Why do you have a 23 byte structure?
The question is, what exactly is this 23 byte structure for? The details are, this is where all the 23 bytes come from. We'll talk about exactly like what all these bytes are doing later. But for now, it's just every row has that, and there's nothing you can do to change that. That's fixed for every row. It's going to be 23. The next example has multiple columns, so we'll take a look at how that affects things. So insert into example 2, 1, 2, 3. So our header, again, 23 bytes for the struct, 0 for the null bitmap, and then add 1 padding. So we get 24 bytes total. The data here, so our small int right here is at position 24. Small int, position 24. It takes up 2 bytes. Takes up 2 bytes is just the size of the small int. And so the next possible location is at position 26. But the big int has alignment. So if we look back at the alignment table right here, nope, not right there, right here. The big int has alignment D for double, has 8 bytes alignment. big int has align equal d equals 8 bytes. So it needs to be at a position that %8 equals 0. And so we need to add 6 bytes of padding. So the 26 plus 6 will get us 32. That will put us at something that %8 equals 0. And so the big int is at position 32. So we have the small int plus 6 bytes of padding, then the big int, and then next comes this integer right here. The integer has a line equals I equals 4 bytes. So it needs to be at a position %4 equals 0. The big int took up 8 bytes. So it's at position 32 and it goes to position 40, taking up 8 bytes. So 40 is the next position that we can be at. 40% 4 is equal to 0, so the integer can be at position 40. So we had, for the small int, 2 bytes of data plus 6 bytes of padding. For the big int, 8 bytes data plus 0 bytes padding. And then for the integer, we have 4 bytes of data. So in total, this is 8, 16, 20 bytes. Are there any questions about how we got the 20 bytes right here? So just going top to bottom is the order that the data will appear in the table, small int, then big int, then integer. And for each one of those, for the small int, the data is the total size of the type. Rerunning this query right here, the type length is the size, the total number of bytes that it's going to take up. -1 means it's going to be variable. So we're not handling that case right now, only the positive ones. Things could be 1, 64, 8, 2, and so on. Int 8 is a synonym for big int, takes up 8 bytes, alignment of D. Int 2, synonym for small int, 2 bytes, alignment of S. And anytime we have a particular column, we have to, the data takes up however many bytes its type length is. And then, so there's the data. And then the padding is needed so that the next type sits at the appropriate position. So in this case, finishing up the problem, we have 20 plus 24 equals 44. That's not divisible by 8. We need to add 8 more bytes to make it divisible by 8. Sorry, 4 more bytes to make it divisible by 8 plus 4 padding will give us 48 total bytes. So this row right here takes up 48 bytes. The second example, the only difference between example 2 and example, or this second insert and this first insert is that the 2 right here is replaced by a null value. And null values don't get represented at all. So here, the header, we have 23 bytes for the struct, plus 1 for the null bitmap, equals 24 total. Almost always going to be 24 total up here in the header. And then for the data portion, here we have The only thing that we have to represent is the small int and the integer. We don't represent the big int in the middle. So the small int, the A, 2 bytes of data, and then the integer needs to have an alignment of 4. So this is right here, position equals 24 up to 25, not including 26. So the integer can't start at position 26. Integer needs to start at position 28, something divisible by 4. So we'll add 2 bytes of padding up here in order to make the integer start at position 28. It has 4 bytes of data. So in this case, 2 bytes of data, 2 bytes of padding, 4 bytes of data, 8 bytes total. Padding down here, the size of the header, 24. 24 plus 8 equals 32. That's divisible by 0, or divisible by 8. And so no padding. So the total, 32 bytes. Any questions about this row, why it's taking up 32 bytes? Is this feeling like overall making sense? Question? Question is, what exactly is the null bitmap used for? There's many things, but one of them is, in this case, in order for us to know that we don't need to store the big int right here, we need some way to know that the value is null. And so the null bitmap tells us that this value is null. And I guess that's the main use, is so that we don't have to actually store the null value somewhere else, that we know when something is null or not null. Any other questions about this problem? Great, example, the last insert over here, 3 nulls. So the header, it's again 23 bytes for the struct, plus 1 for the null bitmap, 24 total, no data being stored. 24 is already 24% 8 equals 0, plus no padding, and so the total total bytes, 24 bytes. On any of these problems, let's see, yeah, so there is one part of checking your work that I'm going to show you. On any of these problems, Postgres can tell you like exactly how much data goes into the header and data portion of a particular column. In order to see how that works, I'm going to open up Postgres. And there is a command right here, pg column size, that gives the size of the header plus data portion only without the padding portion of a particular tuple. In order to use this function, you do select pg, what's the name of it, column size, pg column size, and then you pass in a row type into as the parameter here. The row function creates a row by itself, and then that will be passed to PG column size. Here we have a row that is empty. And so a row that is empty has no data inside of it, but it still has the header information. So it has the 23 padded +1 up to 24. We can create a row that is just like the first row of, or the row of the example table, doing one type integer. So this one type integer right here, this corresponds to the same thing as this insert table right here. This one right here has type integer because it's the first position, so it has an integer right here. This is the same as one type integer. Do enter, and there we get the 28. This is again not the total size, this is only the size of the header plus the data, and so when we add the padding of an additional 4, we'd get the 32. If we change this from one of type integer to null of type integer, then this is what we inserted right here. We have a null, it's type integer because the first column is an integer again. And so now the header plus data is 24. And again, in this case, there's no padding because 24% 8 is going to be 0. If we have multiple columns that we're working with, so like in the second example, small int, comma 2 of type big int, comma 3 of type integer, like that, then the header plus data is 44. And again, this is not including the padding, so we'd have to add the 4 additional to make it divisible by 8 and get the 48. Then we saw with the big int being null, like that, that gives us 32 because we don't have to represent this big int anywhere. And then with everything being null, like that, then it's all the way down to 24 again. Yeah.
What if like you change one of the null values to practical value of the type, like
so if we change a row, change a value in a row?
Yeah, like have like a null value.
Yeah, so the question is, what happens if we change a value of a row? And the answer is changing rows is going to be very complicated internally. All of these header bytes, this 23 byte overhead right here, it's basically all there to support changing and updating, deleting rows from the table. It turns out to be very complicated because we'll see in a couple of sessions that you can have multiple clients connected to the database, all looking at different versions of the database at the same time, that I might delete a row and it might only be deleted for me, but not yet be deleted for you. And how is it going to handle all of that? And so it's complicated, but the short answer is that like things never change. Once something's in a database, you never change it. There'll just be new rows added later that have the correct updated values. Any questions about this PG column size function? Okay, the tricky problems. So scroll down, example 3 right here. Things have been ordered differently so that, and if you work through the results, all of these inserts are exactly the same inserts, just with the columns rearranged to match the new column order up here. And you'll see that the total number of bytes used is always going to be less than or equal, for example, number 3, than they were, for example, number 2. And ordering the columns in your database turns out to be a moderately important task when you have very large tables, like on the order of terabytes, because it will save you lots and lots of disk space and make your operations be significantly faster. The process of reordering your columns is sort of commonly called column Tetris, to make them all ordered properly. And so the main takeaway is that you don't want to like logically group things together. You'll want to follow this procedure right here. Order your columns in a fixed length from largest to smallest, and then use a variable length, all the variable length ones after that. You can see it. So this link right here takes us to GitLab, and this is their like official documentation on how GitLab developers, so people editing the GitLab source code, how they're supposed to write their SQL databases, and that's the formula that they use, and they go through some examples of why that's sort of the correct thing to do. And GitLab, if you haven't heard of it before, it's sort of like a competitor to GitHub for hosting Git repositories. The Postgres developers are aware that this is like, it's a bad thing, that it's not at all obvious that just rearranging the order of your tables is going to change the amount of the performance of your database in any way. And so that's definitely like a code smell or a wart on your code. And so there are people working to fix it. But again, Postgres is very conservative in terms of wanting like things to stay correct. And so because a change like this has to touch basically every part of the source code, it's unlikely to get added anytime soon. But there's ongoing discussion about how to implement it right here. Any questions about anything about column Tetris? Okay, last thing for today, there's this variable length columns, how they're stored. They're stored in something called a toast table. Toast is used for, again, these variable sized columns. It stands for the oversized attribute storage technique. And it's affectionately called the best thing since sliced bread. That's why it's called toast, so that they could call it this in their documentation. The basic advantages of toast is that we can store arbitrary large variable length columns. So most commonly text, but other things as well. Like we can store images or zip files, anything like that in our database, and everything will work perfectly fine. Other databases, that's not true. We also have no particular overhead for doing this. Other databases, if you want to have, say, like a 1 GB column, you have to allocate 1 GB for every row. You don't have to do that in Postgres. There's the main takeaway in terms of designing a database is that in the SQL standard, other databases, you'll see char in and varchar in, where in is like the maximum size that a column can be. These are used a lot in other database systems for performance reasons. They're supported in Postgres just for compatibility reasons, but it's strongly recommended you never use these, and instead always use the text type, because under the hood, they're all implemented the same way. But text is the more Postgres thing to do. Another nice thing about these toast columns is that they automatically and transparently will compress large columns, so typically greater than 2 kilobytes of data for you without you having to do anything. So if you have large data, you're inserting, I don't know, a picture into your database, it's automatically going to compress it for you. You don't have to worry about that. Disadvantages of this toast format, it's rather complicated, so we're not going to talk about it in detail, but there's the docs. And the main like practical disadvantage, there's this problem right here where a null byte, so something that's how you represent it in Python, \x00. The null byte, for those of you who've done C programming before, is the same null that terminates C strings. It's not allowed in text anywhere because since Postgres is implemented in C, it is used as the terminator of all its C strings, and it would confuse a lot of code if you actually included this. So if any of your data contains a null byte, you can't insert it into Postgres. And there's workarounds, but they're sort of a pain. And this is another one of those things that the devs know about and are working on, but because it would touch a lot of areas in the code base, probably not going to get fixed anytime soon. Any questions about Anything related to the rows and how much data they take up?
So are you like all stored somewhere else in the original table, or are they still stored?
Question is, are these text or more generally toastable columns stored in the table themselves? And the answer is sometimes, sometimes not. We'll get into the, so right now we've only talked about like how tuples themselves are stored. A page is a collection of tuples that stores like 10 or 1,000 rows at once. And then a table is takes up a table is stored as a collection of pages. And so we'll talk about the page format in a little bit. There's special pages for these toastable tables or for these toastable columns. Next time, we're going to be focusing on how redundant data can be stored multiple times or just one time, and how that relates to more general database design decisions. And we'll be talking about this concept of denormalization versus normalization of our database. I think that's a good stopping point for today. So I'll stick around and answer any questions that people have about this or about the homework or anything else. And please, again, take a few minutes to do the survey, and we'll, have a nice day.